Okay, let's talk about complex numbers, list some of their properties, and first see why we should care about them. Their role in math is not unlike that of negative numbers, which are abstract objects such that when you add them to positive numbers, you get zero. There's really no question we should be looking at negative numbers just to keep track of debts, loans, money owed. It is a very useful abstraction. Now, imaginary numbers are those such that when you square them, you end up with a negative number, like -1. Now, why we should consider those abstract objects is a little less clear from everyday practice, but the need arose historically from the problem of finding roots of polynomials. And so here, let me give you an example. Here's where imaginary units come up, even though we're dealing with real numbers. Find x, which is a root of the polynomial x cubed minus 6x minus 2. And it turns out that one of the roots of this polynomial has the following formula: x equals a plus plus a minus, where a plus is the cube root of 1 plus square root -7, and a minus is the same formula with a minus sign. So here, in the 19th century, the game was to find such formulas where you had only square roots, cube roots, and radicals. Now, this is a little special because it's not clear a priori what square root -7 may mean. But what we can do is introduce an imaginary unit, be a little fearless, and carry out the algebra with this imaginary unit, so all the plus, minus, times, and divide. And by doing so, we can convince ourselves that this is in fact a real root. This is a real tangible number, and there is a characterization of it using this formula here that have radicals in them. And there is no other such formula. The imaginary unit was needed in order to have such a formula. So this completely validates their introduction. They were needed in order to write down these formulas with radicals. But now the truth of the matter is, in science and engineering, complex numbers nowadays are everywhere. And this by itself more than justifies their introduction. And you can convince yourselves of that by studying things like Fourier series, for instance. So a complex number is obtained by doing exactly what I said, using the algebraic operations on imaginary numbers and combining them with real numbers. And so a complex number is going to be x plus I y, where again I here is this imaginary unit. All we need to know about it is I squared is -1, and x is real and y here is real as well. It is called a complex number because, as you can see, it is a compound of two real numbers. It is a complex of reals. X is called the real part of this number, so let's give it a name. Let's call it z. Then the real part of z is called x, and the imaginary part of z is called y. The real part is real. The imaginary part is real as well. The imaginary part is y. It is not I times y. So keep in mind, the imaginary part of a complex number is in fact real. Now let's go ahead and do a few things with complex numbers. Let's first define the complex conjugation with an overline here. That is the operation that consists in flipping the sign of the imaginary part. So that's x minus iy. That's a complex conjugation. Let's do an example of multiplying two complex numbers that really, again, is everything you already know, and on top of that you have the property that I squared is -1. That's really all you need to be able to generate everything we're going to talk about in this video. So let's do an example where we multiply those two complex numbers. What we do here is we distribute the factors and perform the multiplication. So we have 2 plus 3i, that corresponds to multiplication by 1, and then we have -10i minus 15i squared, that corresponds to multiplication by -5i here. And again, here we're going to use the fact that I squared is equal to -1. And we simplify and we obtain 2 plus 15 for the real part, that's 17. And for the imaginary part, we have -7i. So that's how you multiply complex numbers. Dividing complex numbers is a little trickier. We have to use a bit of a trick to be able to do that. Yes, there is an expression for that, meaning its reduction to real and imaginary parts. And the way that works is you multiply top and bottom by the complex conjugate of the denominator, and that will lead to simplification. So let's see whether that's the case here. We have 1 plus 5i will be the complex conjugate of the denominator. Let's multiply top and bottom. At the top, what do you see? Well, you have 2 plus 3i plus 10i plus 15i squared when you distribute the factors. And the denominator will end up being quite simple. Why? Because we have 1 plus 5i when I distribute against 1 here. And then we have minus 5i when I distribute against 1. And then if we distribute against 5i, we have plus 5i here, and then minus 25i squared. Notice what happens here. Those here imaginary terms cancel out, and we are left with a number here, which is going to be positive. This is I squared is -1, so this is going to end up being plus 25. So we have 26 in the denominator. The numerator will give us minus 15. For the real part, we have 2 minus 15, that's minus 13. For the imaginary part, we have 13i. And in the denominator, we've already seen that's 26. So we can simplify that. This example is a little contrived and chosen so that we end up with nice numbers. 1/2 plus 1/2 of the imaginary unit. So that's how it works. Multiply top and bottom by the complex conjugate to perform a division. This example is actually generic. It is a generic phenomenon that when you take a complex number and then you multiply by its complex conjugate, you end up with something real. So this was no accident that the denominator was real. And why is that? Well, let's do this. Let's use x plus iy multiplied by x minus iy, the conjugate. What do we see? We have x squared, and then for the imaginary terms, we have plus ixy minus ixy, and then minus I squared y squared. So we see that like before, these imaginary terms go away. Negative I squared is 1, and so we have x squared plus y squared. It is indeed a real number, and it is always non-negative. This has a name. This is called the modulus squared of z. So when you take the square root, you get the modulus of z, that's the square root of x squared plus y squared. So that's an important quantity in relation to complex numbers. It's called the modulus. It's fine to call it the absolute value, but you need to know that you're talking about the absolute value of a complex number, and so it's sometimes better to be sure we know what it is by calling it the modulus. If you had instead done the square of a complex number, then you would have ended up with a complex number again. That would not, in general, give you a real number. Why? Because when you distribute, you get x squared plus 2ixy minus y squared, and that has a real and an imaginary part. So the next concepts are best illustrated if we move on to what we call the complex plane, and we go ahead and represent numbers in the complex plane. So how does that work? We are going to view a complex number as a couple x and y. So here x plus iy we see as the couple x comma y, where we report the first component x here on the x-axis and the component y on the y-axis. So here the x-axis is the real part of z, and y-axis is the imaginary part of the number z. So this is z here. This picture is actually really important because it gives us a lot of various properties about complex numbers. It helps explain them. And the first thing we can do is notice that if we have two vectors, z1 plus or minus z2, meaning two complex numbers, z1 and z2, and we add them or we subtract them, the way these additions and subtractions work is exactly like they do for vectors. So like for vectors, you add up or subtract the components of those vectors. If you take a complex number z and you multiply it by a real number a, or specifically a positive number a, that will give you a scaling or a dilation or a compression of that vector. So you just put it to a different scale like you do when you multiply vectors by a positive number. So no surprise there. It becomes a little bit interesting, and that's why we need the complex plane. When we consider quantities such as I times z, where I is our imaginary unit, what does that do? This is no longer a scaling. It's a little more complicated. And so to see what that is, let's go ahead and compute iz. We have ix plus I squared y. So it's ix minus y. And if we want to plot that, let's use a different color here. We go back to the complex plane. We realize that the imaginary part here now is going to be x. So our x we used to have here is now going to be over here. This is going to be x for the imaginary part. And the real part is going to be negative y. So it's going to be somewhere around here, negative y. So now we have the vector here that has those components, and this is going to be our new complex number that is represented by this vector here. This is going to be I times z. And the operation that will give you the green vector from the blue vector is a counterclockwise rotation by 90 degrees. This is a counterclockwise rotation by 90 degrees. So it's not a scaling. Multiplying with a complex number will in general also induce a rotation in the complex plane. You see an example of that here. Another vector that is nice to represent, to illustrate, to visualize in a complex plane is going to be the complex conjugate. So the complex conjugate again is x minus iy. So let's go ahead and see where that belongs in the complex plane. Where is x minus iy? The real part of it is still x, so it is still going to be here, and the imaginary part of it will be negative y, so here it is negative y, and the vector that results from that, components x and negative y, will be this vector here. So this is what is going to be now the complex conjugate of z. Here it is, and the operation that gives you now the red vector from the blue is a reflection about the real axis. Conjugation reflection about the real axis. And many other important properties of complex numbers are obtained in the complex plane. Let's see another one here. For instance, the modulus is visible here from the complex plane. It is the length of the vector here between the origin and the point z. So that's where the modulus can be read here in the complex plane. Okay. Now, a few more properties for complex numbers. Let's talk about inequalities. It is never okay to write inequalities such as z less than 3. That makes no sense. It did not make sense for vectors, and it does not make sense for imaginary or complex numbers. So do not write things like this. However, so let's go ahead and cross that out. However, what would make sense if you wanted to write an inequality with complex numbers would be something like this, which says that z belongs to the disk centered at the origin with radius 3, for instance. So writing that modulus satisfying inequality is perfectly fine. Now here are a few more facts that are important when we do algebra with complex numbers. The real part of a number z can be obtained from the sum of a number, its complex conjugate, and then divide by 2. The imaginary part of z can be obtained by taking the number, subtracting its complex conjugate, and then dividing by 2i. If you take a complex number, you conjugate it, and then conjugate that again, you get it back. No, visually you can see that as taking one reflection and then going back. That's what it would be. What else? If you have products of complex numbers and then you take the modulus of that, you can obtain that by taking the product of the moduli. And if you divide two complex numbers and take their modulus, that will be the ratio of their moduli. Now, this is by no means obvious, but I'm listing those properties for you, proving that from what we've seen so far is not going to be straightforward, but it's true. And in fact, something very similar happens if you want to take the complex conjugate of the product of two complex numbers. Then you just multiply the conjugates, and if you take the conjugate of the ratio of two complex numbers, that's going to be the ratio of the conjugates. And finally, an important role that complex numbers plays that was alluded to earlier is in finding roots of polynomial. If you have a polynomial of a complex variable z, so again the roots are those numbers z such that when you try the polynomial you get 0. And complex numbers play a very, very important role in finding roots of polynomials. Let's take an example here. Let's take p of z to be the polynomial equal to z cubed plus z squared minus z plus 15, which happens to be factorized the following way. This is not something that you can easily eyeball at all, but it happens to be true. And once you have a polynomial in factorized form, then you can tell what the roots are. They're going to be the numbers for which one of the factors is 0, and therefore the product is also 0. And here in this case, the roots are going to be -3 or 1 plus 2i or 1 minus 2i. Either of those works. And this situation is generic. It will always be like that. If you have a polynomial of degree 3, it will always have 3 roots if you're willing to consider complex numbers. The roots may not be real, but there will always be 3 roots. And in fact, this is a very general phenomenon that happens with polynomials. We can call that a theorem, that if you have a polynomial of degree n, then automatically you know that it must have exactly n roots, but those may be complex. So it's going to have n complex roots. This is a very important result in mathematics. It takes the name fundamental theorem of algebra. Another observation we can make in the case of a polynomial like the one we chose here, it is a polynomial that has real coefficients. The observation we can make is that if you have real coefficients in your polynomial, then the complex roots do not occur any old way. The way they occur is always in complex conjugate pairs. So here you can see 1 plus minus 2i, and that they cannot occur any other way if they're complex. The roots occur either they're real or they occur in complex conjugate pairs. Now at this point, this is where we would want to take a look at a few examples, like for instance, p of z is equal to z to the fourth minus I. For instance, here you have a complex, an imaginary number as one of the coefficients. It is not easy from what we've seen so far to find what the roots of this polynomial would be, but this is where it's important to introduce a so-called polar form of complex numbers and to introduce complex exponentials. It's not going to be in this video, but it's going to be in the next video.